Good morning, ladies and gentlemen. Welcome back to the second day of this conference. It's my great honor to introduce today's Chinese speaker, Professor Irene Fonseca. Okay. She was born not a long time ago, okay? And then she got in Lisbon, Portugal. And then in 1985, she got her PhD in University of Minnesota. From 85 to 87, Professor Fonseca has a postdoc position in Paris, École Polytechnique. She then became an assistant professor in Carnegie, where she promoted to full professor in 1989. In 2003, she was appointed the first Mellon College or Science Professor of Mathematics. Okay, first one, right? She has delivered a PhD 2006 AWM and Science Sodium Coalescence lecture at the Science Annual Meeting. That's very prestigious one. And has been elected to be a science fellow, the first class. Okay? So currently, she's the director of the Center for Nonlinear Analysis, which is the NSF funded in Carnegie, and she will be the science next president for next January. So let's welcome Professor Fonseca.
So I would like to start by thanking the very kind introduction and thanking Professors Chen and Min-Si Lai for this invitation. I'm honored to be here. And it's the first time I'm in Taiwan and hopefully not the last. So anyway, it's delightful to be here. So what I'm going to talk about here today is you can take it a little bit like a tour of some of the problems that we are studying in my group. And so there will be no proofs. There will be a few statements of theorems, but basically what I want to convey is ideas of some of the challenges that we are facing and how mathematics is powerful in that the same set of tools and sometimes the same type of models can address completely different issues coming from the applications. So, and what I want to talk about here in particular today is concerns energies that have several peculiarities and that their study cannot be undertaken using your traditional tools that we are used in classical theories, but they force us to think a little bit out of the box. And actually, for those of you who followed the talks yesterday, in particular of Professor Min-Si Lai, and also during the section on PDE, you've heard about problems that involve energies which are actually bulk energies competing with surface energies, for example. You heard about interfaces being driven by different types of motion like surface diffusion, and you're going to see that here in my talk today. So the energies I'm going to talk about will include both bulk and interfacial energies. The underlying fields often will not be scalar valued. They will be vector valued, and life is different when you go from fields, and if you think, say, in terms of Sobolev spaces, with values in R or values in R3 or values on the sphere, things are different. Also, although the calculus of variations is very well developed and very well understood for functions involving first-order derivatives and only up to first-order derivatives, that's not true if you go beyond first-order derivatives. If you start involving second-order derivatives and higher, life changes. And so you cannot just take what you've learned and say, well, okay, it will be the same. No, it's not the same. There's a lot more rigidity because you're working with higher order derivatives. And also, often your underlying fields will not live in your comfortable Sobolev setting because they may have discontinuities. And so you may have to deal with, say, function space of bounded variation or bounded Haitian or things like that. And again, that will force you to think a little bit differently. Okay, so why do we care? Well, first of all, because of course mathematically it's all very interesting, and that's why probably most of us are here today. But also, I like to think that one day this problem surfaced because there was some relevance to the world where we live in, and hopefully, who knows, maybe one day we can close the loop and they can be helpful to exactly resolve some of those issues that we deal with. And in particular, in my program, I worry about several issues, and one is that imaging, and I'm going to talk about here today. Epitaxal deposition of films over substrates and the formation of quantum dots. I'll talk about here today. If I had a time, I'll talk about foams and surfactants again. That goes back to last evening's plenary talk by Professor Mincelai. I don't think I have time, but okay, let's see how it goes. Micromagnetic materials, materials really interesting, ferromagnetic and micromagnetic properties, nanomaterials, very thin structures, and so on. Okay, and I highlight in red because at least I'd like to go over the first bullets here today. And again, the message that I want you to take from here today, if nothing else, is that here are very different areas of applications, and at the end of the day, the models are basically the same, the mathematical difficulties are basically the same. And again, I like to think that's one of the power of mathematics, is this level of abstraction that let us go to another sphere and abstract from that, develop complete theories and tools, and then go back to the applications with what you've learned. Okay, so let me start with imaging. And I'm going to, in the beginning, talk about black and white pictures. By black and white, I mean black and white and levels of gray. So you have to think of that as your input being a function that lives on the square of your frame of your picture and takes values in 0, 1. 0 is white, 1 is black. In between you have levels of gray. And in particular, there is a model which is the Rudin Osher Fatemi, ROF for short, model that's been very well used. And this model develops what's called the staircasing phenomena, and one way to resolve that is exactly involving second-order derivatives. Remember, it was one of the bullets I had in my first slide, that sometimes you have to go to second-order derivatives and higher. So you go back to second-order models. I'll talk about denoising. But life is not in black and white. Life is in color. And if you talk with people in artificial intelligence and computer science, they'll tell you depth is important to resolve pictures, and depth is related to having colors in your model. So black and white are very flat. And heavy colors, there are several models. I will talk about the RGB model. RGB standing for red, green, and blue. These are 3 channels, and that's usually used in image segmentation and colorization in computer science. So here it is. So now you're going to leave from black and white pictures where your field has values in the interval 0, 1, scalar value, now to R3. So remember, it was one of my bullets that sometimes you have to go to vector valued functions and life becomes different. And I'll talk about reconstruction of images. So let me start very briefly with the Mumford-Chow model, black and white pictures. What you have here is a model that is going to let you denoise a photo, a picture that is given to you that has a lot of noise in there. That's F. So F is your data, and I want to stay close to F, so I'm going to, when I minimize this functional, this is called the fidelity term. I use the L2 norm, I could use any LP norm. So you will try to stay close to the image I'm going to give you, which is F. By having grad U, that means that every time I have gradients that should not be there, blurred regions, this term is going to penalize that. So you don't want to put huge gradients if you should not have them there. And this stands for, S of U stands for the singular set of U. U is going to be a BV function, so it can have jumps. So that's the jump set of U. You have traces of U on each side of the jump set. Nu is a normal to the jump set. Take these to be 1. So that would be just, this is just Hausdorff measure. Say if you are on the plane, N is 2, this would be just the length of the interfacial set. So that's another term that penalizes jumps. So if you should not have jumps there, don't put them there in your energy because this term penalizes. So you have a competition between having jumps or having a smooth transition between zeros and ones, right? You have a competition here. Why do you want to stay close to F? Because of this. By the way, as I move along, I have some names in there of people who have collaborated or have participated in this. It's by no means comprehensive. There are more names in the list, but there are a few to start with. So let's look at this very simple Muffer-Chow model with P equal to 1. So if you go back, take P equal to 1. If P is equal to 1, normally you don't need to put this term there because when you relax from W11, you know you are ending in BV anyway, and you're going to produce a singular set, a singular measure there, right? So this is just a total variation measured on interval AB. That's your fidelity term. And it turns out that if your initial image is non-decreasing, say from 0 to 1, the unique minimizer of this model is actually something which looks like your initial image, the one I give you. Most of the time, it's flat, it's a constant up to F, then it's F, then it's another constant. What these constants are does not really matter. You can actually find them explicitly, but the bottom line is that if your initial image is non-decreasing, when you minimize these, you basically recover most of the time what I gave in the first place. It really does not denoise or detexture, does not do much to it, right? So that's, and actually what you have here is a cartoon of what you get by using the rough model. You can see a lot of spurious and edges there that should not be there. That's what we call the staircasing effect. What you see on the right is what I'm going to obtain by adding a second order derivative to the model. And I hope I can convince you that this looks better than this. So a lot of these wiggles disappeared in here because we put now a second order derivative, and I'll tell you that in a second. But let's go over the staircasing again. Take F to be just identity. Well, it's very non-decreasing, right? It's f of x equal to x. On top of that, put some noise. HN, HN goes to 0 uniformly, so the noise is really very small. If you put on top of F, you have these staircases. F now becomes a staircase. But if you look at the theorem we had before, this is a non-decreasing function. So it says that for this data, the minimizer of the rough model will always look like UN most of the time. Looks like UN most of the time, except for flat part, then it's these wiggles, then it's another flat part. And by the way, the flat parts are not going to disappear. They actually converge to some constants. So you can wait forever, the wiggles will never disappear, because in a big part of it, you always have this Fn, which is all jagged. That's not good. So that's what you do so you're going to add second order derivatives. There are many models. Blake-Zimmermann is one. That's not what I want to talk about here. Many people have worked on that. Names that you can recognize like Lyons, Chan, Tony Chan, and others, Osher. But I will talk about this particular model that was actually introduced by Tony Chan and his co-authors at UCLA, when he was at UCLA. And so it's basically the rough model, total variation, plus fidelity term, but now I'm going to add a second order term. And this second order term is such that the psi that I put here is 0 at infinity. And what that means is that if you have a true edge, that is, the gradient is basically plus infinity, going from a 0 to a 1 very sharply, then this is 0, so this term does not mess up true edges. If you have a true edge, this term will not see it. It's 0. But if you don't have a true edge, and you start having lots of transitions, this does not like it. You have a second order term. You're going to have a huge penalization there. Okay, so that's what it is. Here I don't put the fidelity term because in terms of the calculus of variations, it's a compact perturbation, makes no difference. So keep just the total variation, keep the second order. By the way, people in computer vision use this particular psi because it's just a curvature. When you plug it in there, it's exactly the curvature. And as you can see, it goes to 0 at infinity, right? So it's good. It goes to infinity and it does the job. And so we went through this program and we proved that the problem was well posed. We proved compactness. We looked at the effective energy, that is, take all possible ways of approximating your image and minimize over all these possible sequences that's your effective energy, and we could actually characterize what that was. And we could prove that indeed, with the second order, you eliminate staircasing. Not only I gave you a cartoon of that, a simulation, but analytically, you can prove that if on top of F you put a noise, that goes to 0, and it doesn't even have to go uniformly, even just weakly star is okay. Then after some time, you approach, basically what you get is a very nice approximation. It's actually still one approximation if p is bigger than 1. So that's good news. Okay, what about denoising? So this is work with Russell Choksi and my postdoc Barbara Zignagel. She's now in Bonn. So again, I give you an initial image F0. On top of that, I put H is noise. And I would like to minimize and reconstruct my clean F0 and get rid of the noise, right? So if you think about the rough model, which is, well, there's a fidelity term plus a total variation that's basically penalizing transitions where you should not have transitions. I can actually think of an abstract formulation of that and think of some semi-norm on some Banach space plus a norm on some, say, LP space. So you can think of that as, again, Y could be like a LP space. This was BV, but it could be a more complicated space, could be actually Sobolev space or something like that. So what the two questions that you ask are, so if I take the fidelity parameter large enough, do I actually get the exact F0? Does this completely erase the noise? One, and second, it's a stability question. So if I add to F0 a sequence of noises, if n goes to infinity, do I recover in the end F0 again, right? So let's look at stability. So I take a sequence Hn that goes to 0 in some weak sense. So to my F, I added now Hn, so now that's your initial input. This is the one you want to get at the end of the day without the noise. And you'd like to know that minimizers of this functional converge to minimizers of the undisturbed functional J. But more, you'd like to know that you don't have to wait forever. You'd like to know that after, for large n, actually they are exactly the same minimizers. You don't have to let n go to infinity. The bottom line is that no functional is good for both questions. The ones that I asked here, 1 and 2, some are good for 1, some are good for 2, but as far as I know, no one actually does the job for both simultaneously. Okay, and you can prove that, let's go back, beta is the exponent of the fidelity term. In the rough model is 2, and you can prove that if beta is bigger than 1, and if your initial signal is non-zero, it will never be recovered. It will always get something else, but it's not F. That's not a very good. And again, for Roth, that was 2. That's right. So, and by the way, and if that is 1, if F is smooth and it has a strict local extremum, again, it will never be recovered. So that's not good news. On the other hand, if you now look at asymptotics, when you put this noise that goes to 0, it turns out that very bigger than 1 is exactly the right regime. And so L2 square, for example, is very good. And so this analysis uses gamma convergence techniques and a very easy lemma by Brizes and Lieb, which it's in here. But anyway, it shows that for beta bigger than 1, you can actually remove these problems. Okay. And indeed, minimizers converge to the minimizers, and in the right sense, and you can have all kinds of different norms for that. Okay, but now I want to move into, so that's all I want to say about black and white. There's a lot more to say about that, but I want to move into color pictures. And now life is going to become more interesting because it's in colors, right? So, and one of the things I'd like to do is to look at restoration. You can think about this in 2 ways, and one is this. Suppose that, and maybe I have a cartoon here. Here it is. So what you're looking here is a fresco. It's a piece of a fresco that was taken from a chapel in Padova, in Italy, that was bombarded during the Second World War. And the chapel is called Ortari Chapel. And bits and pieces of these fresco were laying on the ground for decades. And of course, some of them were protected from the sun and rain, but others were exposed. So in bits and pieces, you still had color, but a lot of it was just levels of gray. You had the contour lines, but you only had gray levels. And the question is, can you reconstruct from the bits and pieces of color that I give you here, color everywhere in your picture? So that's what we call recolorization. But you can also turn this problem upside down, which is this. So suppose that I'm on this part of the world, and I took a picture, and you can think of this in terms of defense, and I'm not saying anything that's classified, but think, so let me put it in terms of, say, from the tourist point of view. So I'm here, I took a picture, it's beautiful, it's in colors, and I want to send it to the United States really, really, really fast. It has to be processed really fast, but colors take a lot of cyberspace. So I should give you pixels, whites and zeros and ones, give you just a little bit of color, the rest in grays, under the assumption that on the other side, you'll be able to recover it with maximum fidelity, just by giving a little bit of color and grays and contours of gray, you can recover color everywhere. How can we do that? Okay, so let's use the RGB model. By the way, that's not the best model for these, and I'll come to that in a second. But, okay, you do what you can. So R is the rectangle of your photo, so it's a rectangle on the plane, right? That's the domain of your picture. U0 is going to have the 3 channels, red, green, and blue. And every time that you have a pixel with color, you can transform that into a pixel of gray levels by contracting the 3, usually by making the inner product of your color with a unit vector on the sphere. Usually we take E to be a third, a third, a third. Giving the same weight to the 3 colors works pretty well most of the time. Again, it depends on the setting. If you're working with medical imaging, it would be different. If you work with the brain, if you work with the heart, it's different. But for most purposes, a third, a third, a third would work. So that's a way of mapping R3 into R, so colors into gray levels. So associated to the color everywhere, there will be a gray level. But so on your rectangle, there is a sub-region, which is a damage region, D for damage. And that's the reason I have to in paint, where I have to put paint in there. I don't have paint in D. So I observe two things. Outside D, I observe color. In D, I'm only going to give you gray levels. Okay? And so if you think of, if you knew the color everywhere, then V0 would be L of V0. That's the second setting. When I know the color everywhere, I'm going to send you the picture just with color somewhere, so I know already U0 everywhere. So again, most of the time, a third of the sum, it's just averaging out works well. So this is the goal, produce new color that extends the colors from the pieces you have everywhere. Okay, again, Maffer-Cha model, rough model, right? That's pretty much the Rocher-Offer-Fatemi model. You have total variation that's going to prevent to put jumps where you should not put jumps, where you have high transitions where you should not have high transitions. It's just total variation. And now you have two fidelity terms, right? One is, so outside the damage region, when I give you color, you want to stay close to the color I give you. In the damage region, the U that you're going to produce that's going to have color everywhere, see U has values in R3 everywhere, but in the damage region, the gray levels, when you collapse it into the gray levels, should be close to the gray levels I give you, okay? And these are fidelity parameters. So this was studied by several people, and I should tell, and more recently, but I should tell you that I'm using the RGB model. A lot of people in computer science will tell you that RGB models sometimes produce a lot of shadows, and they are not that sharp. And you do better using the so-called brightness chromaticity model. Instead of representing a color with 3 channels, you then represent a color with a vector on the sphere and a parameter, which is the color and intensity. So you have, basically, you're working in a Sobolev setting with values on the sphere and a scalar and an LP function with values in R+. And again, as you all know, Sobolev settings, Sobolev space with values on the sphere are not that easy to work with. And so there's a lot to be done here. I'm not going to talk about this today. But I have work ongoing with some of my postdocs. Okay, you may ask 2 questions here. One is, what is the best D? So how much color should I give you and where so that you can reconstruct the full colored picture with maximum accuracy? Let me move on. So what I'm giving here is simulations of the model I'm going to use. And I hope I can convince you, at least to those in the back, that I'm not giving a lot of color here. It's mostly grays, right? But for those in the front, you probably see that I have a lot of little dots of color here. It's not a lot, but it's not bad here. And actually, if you look in my laptop, which is somewhere there, but actually the resolution is better than this. It's pretty good resolution. So we must be doing something right. Okay, so that's a model. And now let me do something. Let me be very bold and say, look, I'm going to be really, really drastic here, and I'm going to want maximum fidelity in that I'm going to take these lambda 1 and lambda 2 to infinity, in that I will want you to be exactly U0 on D and keep the same gray levels, right? So that becomes a simplified model. I'm not saying this is the whole story. I'm just giving you a glimpse of a particular question you may ask. So now I want to minimize the total variation, where I want the color to be exactly the color I give you on outside D and the same gray levels. The first, and we say that U0 is reconstructible if it's unique minimized. And better be unique, because if I send you the picture and you find 2 or 3 minimizers, you don't know which one you should choose from, that's not very useful. So you should get one and only one, okay? So that's the problem. And so finding one minimizer is not a big deal. That's just basic geometrical measure theory. But I want to get just one. So let's look at this cartoon here. I give you a piecewise constant image. By the way, most of the time, you can think of them as piecewise constants. So that's not a big, very bad. And I'm going to mess it up here. I only have gray levels here. And I want to reconstruct color everywhere. Now, of course, the first part, and you think of it in terms of the frescoes, the first place where things are going to get bad is exactly on the transitions, on the interfaces between colors. That's probably where the first damage is going to occur. So you want your model to be robust at least when you mess up what's going on around the contour. Okay, so R is the gamma with the union of these omegas, and you note that's the characteristic function of omega k. It's a constant on each one of those domains. So I want to minimize there. You can even ask more. You can even ask that not only it's reconstructible, but if I keep the same regions and just move a little bit the color, I still want to have these reconstructible. Okay, so answers. If two neighboring colors are mapped into the same gray level, it's very easy to prove with an example that will never have reconstructibility. However, if not, then you can get some analysis to give sufficient and necessary conditions for reconstructibility. So that's a very simple example. Suppose I give you this is the image I have. Okay, that's what I know. It's yellow here, it's blue there. Suppose that these two colors have the same gray level, and that's the common gray level. This is what I'm going to give you. And I'm going to ask you to minimize the total variation and tell me if you can reconstruct this. And you're going to say no, because if I minimize the total variation, I know that the colors, where I have colors, should be the same. So I know that yellow should be kept there, it is. Blue there, well, it's in there. And now this region here, whatever I put, should be mapped into the same gray level. But if the two have the same gray level, why not put blue all the way there and yellow here? It minimizes the total variation, which is the perimeter in this case. And of course, the perimeter here is much smaller than that perimeter there, so I'm better off with this image. And that's not the one I gave you. So two colors with the same gray level is bad news. Okay, so let me move on. So here is now, let's use PDE to say that to get necessary and sufficient conditions. And if the damage region is one that it's a Lipschitz, then you have reconstructibility if and only if you can find what we call a calibration, which is a field that's divergence-free and satisfy this Neumann condition on the boundary of your damaged domain, and it has L infinity norm less than 1. In terms of Euler-Lagrange equations, basically this was your functional. Your Euler-Lagrange equations it's basically the one Laplacian, and of course not well defined in general, and so basically what I gave you is a weak formulation of this. Okay, so that's basically it. And as a side remark, since you are on the plane, as we know, divergence-free and being a gradient are basically the same up to rotation. And the calibration result I gave you can be thought of as a Lipschitz extension of a vector-valued function, keeping track of its L infinity bounds on the gradient. As far as I know, that's the first such result. You can think about McShane and Whitney's and all these extensions of Lipschitz functions with vector valued, but usually you keep track of the Lipschitz constant. This constant is usually strictly less than the Lipschitz constant. So as far as I know, that's the first such result. But that's just a side remark. Okay, so let's go back to our reconstruction. So cartoon here, and if you remember what I gave you, this is basically what you have here. It's gray levels with pixels of color. That's one cell where inside I'm giving you the color, gray is in there. And that's what I want to reconstruct. And by the way, they don't have to be squared, but the eccentricity should not go to 0. So they cannot be needle-like where you put the color. And Okay, the first result is that if I give you color in regions like that one, like basically the damaged region is between the big cube and the cell inside, then minimizers always go to the true minimizer. And better, that if I have enough color, so if the ratio of W epsilon over epsilon, of course if it goes faster to 0, but not too fast, then actually I don't have to wait forever, but after some time I get exactly, the minimizer is exactly U0, so I can stop the clock somewhere. And this is optimal. There is a counterexample that we can show that if you don't give me enough color, then you'll not get reconstructibility. Okay, so this is basically all I wanted to say about, and I have about 10, 15 minutes to talk about epitaxial deposition. So what I talk about here, I'm just scratching the tip of the iceberg on these problems on colorization and image segmentation using these functionals that involve both bulk and surface energy and the competition between the two, which is basically what you're doing here. So let's now take this to a completely different setting. And what we're going to talk about here is this. So let me take you to this. So you have a substrate, say for example silicon, and I'm going to put on top of that, I'm going to deposit a film, very thin. So usually you model that by saying that this one is infinite in that direction, and this is very thin. So the film has a certain profile H, and so for example in this case it would be silicon germanium, and until you reach a certain thickness, although the substrate and the film have different crystalline structures, and so they are not very happy together. So there is some elastic strain developing between the two. They are a bit uncomfortable, but until you reach a certain thickness, that's okay, they coexist like that, and the film remains flat. It's minimizing surface energy, right? But after some time, if you increase the volume, then the strains increase, and to release these strains, something is going to happen to the film. And it's going to develop islands, or so-called quantum dots. And then you're going to have a competition, because once you start having that, now you're no longer minimizing surface energy, right? Because now you have a corrugated surface. So now I'm going to have a competition. So wait a second. On one hand, I want to minimize bulk energy, elastic energy. On the other hand, I want to minimize surface energy. How can I do the two together, right? So, so let me go back. Several questions arise here. And one is, these islands, when they form, it's known from the practitioners that when they meet a substrate, they meet in a very smooth way. That's what they call, if you read a physics review, you will see that they say it's a zero contact angle, which for us would mean that the profile H is, say, at least C1. Not Lipschitz, at least C1. Okay? Zero contact angle. Second, it has been observed that it has been observed that actually although the substrate seems to be exposed, actually in terms of the energy in the lab, it looks like if it's film that stays there. That's why we call wetting. Wetting because the substrate remains wet. And indeed, we can prove analytically that there is a couple of layers of atoms of film that stays within the substrate, although to your naked eye, the substrate seems exposed. And we can validate that rigorously. Then you may want to ask, what can you say about the shapes of the islands? By the way, you don't want to get rid of these islands. The quantum dots, that's what makes your laptops work. That's what makes them to not overheat. So you want to produce quantum dots in your hardware. The thing is that you want to produce them in particular locations with particular shapes. Different shapes have different technological applications. And so what can you say about the shapes of islands? For example, with respect to the misfit. So if the two lattices are different from with a very high misfit, does that influence the shape of the islands? Or, for example, the volume, the more film I put, will that influence the shape of the islands? And we have an answer to that. I probably won't have time to talk about that. And then there's also a question of, okay, now this is all quasi-static, and now let's let this thing move. And it moves by surface diffusion. So how can we put that into a mathematical framework? So, okay, so this is basically what I was telling you. So lattice bit fits into strains. And in order to release the strains after some critical thickness is reached, which is basic competition between bulk and surface energy, quantum dots form. And they start as pyramids, they evolve into so-called domes, and then the last shape is called a barn, and a barn looks like a mushroom. When you reach a barn, you don't have any more a graph, and your model breaks down. And by the way, this is observed, so it's not just a problem of the model, it's actually reality. Okay, so why do we care? So we have many applications for quantum dots, and again, I told you that these are some of the things we want to explain: wetting phenomena, the zero contact layer. Here's the cartoon. You have the substrate, you have your island, and you have the misfit forming, and as you get there, things are really getting bad, and at this point something is going to happen, but it's a very nice situation where you can have your smoothness there happening. So this is your domain. By the way, I'm going to work on the plane. This should not be done on the plane because these islands are not self-similar away from, say, the board. But all the analysis we have done, it's on the plane. So so the film is between y equal to 0 and y equal to h of x. That's the profile of your film. And you have a Mitchell mass strain. By the way, this is all linear elasticity, very small displacements. So below on the substrate, it's happier when you do nothing. So displacement 0. But on the film, it's happier when you have a shear. So your E0 is the amplitude of the shear. I is, for example, the vector 1, 0. So you're shearing in that direction. So that's a typical positive definite for third tensor linear elasticity. E is just a symmetrized gradient. U is a displacement. And again, you're happier when you do nothing on the substrate, and you're happier when you shear on the film. And of course, the two things don't like to be together, right? So bulk energy plus surface energy. Gamma H is the surface of your film. It's a free discontinuity. Phi naught, here I'm just taking it to be basically isotropic on the film and on the substrate. Does not depend on the normal. It could depend on the normal, but here I'm simplifying. So it's a constant if you're on the film, it's another constant if you're on the substrate. And this is a sharp interface model that's very hard to implement because you have a discontinuity. So what you usually do is you smooth that out with just like a hyperbolic tangent or something like that. So nearby the transition layer, just have a smooth transition between one and the other, but that's just a technicality. So, okay, so I basically smooth out that one and this one, so I don't have a sharp transition. Okay, and if the density of the film is less than the density of the substrate, you can prove that indeed you have wetting. So when you relax the system, you can prove rigorously that relaxed surface energy, the effective surface energy, will not see the surface energy of the substrate anywhere. And what you get actually is a thin layer, a couple of atoms layer of film everywhere. So it's more favorable to cover the substrate with film than letting it exposed. And you can prove in terms of this contact angle that actually it's very smooth. And it's smooth except for at most a finite number of cusps or cracks that could form in your film. The good news is that we can prove that if they are, they're only finitely many. So you cannot have a collapse of your system, so with lots of cracks collapsing, accumulating in some points and in the boundary. The bad news is that you cannot avoid them. And actually, for a long time, we were trying to get rid of these finitely many singularities in your profile, until we were told by a colleague of ours, Bob Kahn, that, wait a second, don't get rid of them, because they do exist in practice. And he had just read in a chemistry paper that indeed they are formed. In some materials, you do have these cracks forming. So, but again, if they are, they're only finitely many. So, but we could prove the zero contact angle. Now, in general, if you don't say anything more, you can only prove that the graph of H is Lipschitz, again, away from these cusps, but you want more than Lipschitz, right? Because Lipschitz is not necessarily zero contact angle. It could be, you could have a corner there. So, but if you ask more, and if you go to linearly isotropic materials, for example, where then W takes this usual form, right? These are just the Lamé constants. Then you can prove better. You can prove that away from the singularity, actually, and these are the cusps and the cracks, actually you have more than C1 sigma regularity for your profile, and that's exactly what the physicists were looking for. Okay, 3D case, well, it's not done. And the analysis that we have done is completely 2D. So you cannot generalize what we have done to 3D. But let me just, in the 3 minutes or so I have left, very briefly talk about surface diffusion. So Einstein evolution law, normal velocity is proportional to the tangential Laplacian, right, of the chemical potential. The chemical potential is the first variation of your energy. By the way, here, I'm even being a little bit more courageous, and I'm taking an isotropic surface energy. So that is the angle of the normal, right? So I'm taking a phi, which is not necessarily constant, but depending on the orientation of the surface. Okay, so this is what you get. That's your, okay, take C equal to 1. Okay, it's just normalizing the constant. K is the curvature. Sigma is the tangential derivative. U is elastic equilibrium that corresponds to that profile. If phi is very anisotropic, and it could be because you're dealing with solid materials, so there's a lot of anisotropy in your system. The wolf shape is usually a polyhedron, polygon. So this could be negative, in which case you have this is a backwards parabolic. It's still defined. So do what everybody else does. And add to it a small perturbation, which is basically you go to your functional and add a little epsilon times curvature squared. Okay, this is old. Goes back to John Kahn and Gene Taylor and many others. It's not a new thing. So add that, and when you look at our Lagrange equation, that's what you get. Now, this is 6th order parabolic equation, because you have 2 derivatives on k, it's the mean curvature, plus 2 derivatives, that's 4 derivatives, plus 2 derivatives, that's 6 derivatives. It's horrible. So, okay, so now let's see what we can do about that, and let's see if we can study existence and regularity for this. And we used, I have 1 minute left, we used minimizing movements, we used the Georges, and I don't think I have time to talk about that. Let me just say that in terms of shapes of islands, we did that with postdocs Patelli and Signagel, and we proved that indeed the shape of the island evolves with the size, and again, becomes as a half pyramid, pyramid, half dome, dome, half barn, barn. And this is what if you look again at physics review, it's in there. It's a 2-page paper for them. It's a 30-page paper in arXiv for us. But it's validated. So, and I think that's probably all I want to say, and I used all my time. So thank you for your attention. Okay.
Can you go back to the...
Sure.
And so when you add it on the red term...
Yeah, which is the variation of a band.
Yeah. Looks, seems to me that a bending of the surface for me is any the physical reason.
Yes, that's exactly what it is. Yes, and that's exactly why I put the k-square there. It's
okay.
because you want to take into account bending.
Okay.
Yes. And actually, okay, and I should add to that that there is also a whole question that's very much related to this, which is to try to understand in terms of coursera theories what happens to the bending moment, and which is underlying here, but that would be another talk. So.
In the phrase called Mantegna, you have this great picture that's taken before the wall.
You mean in the imaging part?
Yeah, yeah.
And the question is?
The Mantegna's fresco in Padua.
Well, the fresco, yes. Oh, I should say, by the way, that it has been restored. And it has been restored using this method. I was not involved, but Fornassi was involved. So they were actually, so if you now go back there, you don't see that anymore. It's all been painted and restored. And the good thing is that there were pictures of course, I mean paintings of that before it was bombed, right? So they actually could check one against the other, but they use the technology. They use this model to actually do it, but they went back and forth and they checked back. So that's it.
But if they have picture, why bother?
Well, that is true. That is true. But the picture will not give you all the nuances. While with you can do basically can go all the way to the. I mean, you can do it with the. It's much more precise, right? Otherwise, you can kind of figure out. Well, maybe it stops there, and then I have to change the color. So, but they could see at least with the naked eye that they seem very accurate.
But it's not open, right? But last time July was there, it was not open. It's just recently done.
The chapel?
Yeah.
Oh, it was done after the year 2000. So it was 2003, 2004. Yeah. So it's been maybe, it's been 5 years or so, yeah. But it's done. It's done and it's all repainted and reconstructed.
About the regularization is in painting pattern. Now you have you add a term which is a second derivative.
Yeah. Oh, for the staircasing, you mean?
And but for staircase, you can also why you have to go to second order instead of first order, but with some power, another power, and also a weight, which is also has it's also concentrated on the.
Okay, so you'd say, for example, go back say, to Mumford Chow, where I would put a gradu to the power p, and then add, but I would have to add a jump term, right? Because otherwise you stay within the Sobolev setting. It doesn't really matter, because actually, even if you put that, you still see. I use a rough model as an example of staircasing, but even with P, even with the Mumford Chow model, you still see staircasing. It won't get rid of staircasing.
P equal to 1, you get staircase.
Yeah. Right, okay, but what I'm saying is that although I didn't do the analysis, but we believe that even with the Mumford Chow, which is P equal to 2, but adding the jump, the length of the jump term, I still think that you still get the staircasing. It won't get rid of the staircasing. And I think even maybe even if you just take the same model, which is like, even the same example, which is take the identity, put on that little bit of wiggles, I still think that you'll get it. You won't get rid of the wiggles. I really think that you need to do something more, and it has to be a higher order penalization that says, well, this is really bad. I'm putting a lot of wiggles in these. And second order, it's probably better than first order. First order does not care much about that. But second order sees it will penalize hugely once you start doing this.
Okay.
In the alpha model, optimal lambda is the Lagrange multiplier. There's only one correct lambda. In that particular lambda, does the staircase diminish or stay the same?
Right. Okay. When I talk about the fidelity parameter, right? Actually, I have to say the fidelity parameter. it is a Lagrange multiplier to some extent, but actually in practice, people play with the lambda, and if you look at simulations, they take lambda all over the place. And then they fine-tune the model to the lambda. So there is, of course, an optimal lambda for which you get a better result. And there's actually quantitative results on that. And for example, there's work by, the work I've done now with Zignagel and Rost and Chuxley. By the way, I should say, a lot of what I said you can find in the website of in the CNA website publications. A lot of it's there, and also presentations. We have a link with presentations, and a lot of this stuff is there. And we have actually a formula for the right lambda that will give you the best result. So
in that lambda, you see the staircase?
Oh, you still see the staircasing if you have first order derivatives. No way you can get rid of that. No.
Okay. One last question. Okay.
I'm not going anywhere. I'm staying here until the afternoon.